To prepare for EDX analysis, mount and pump down your samples as though you were beginning an SEM session, and then find your region of interest. Here, I have a mineral sample that is embedded and polished. So I am operating in the VPSEM mode, the variable pressure mode, optimized for a vacuum setting with the backscatter electron detector. I've chosen accelerating voltage of 15 kV for my imaging and EDX analysis. This is a commonly chosen accelerating voltage for EDX in particular, as it will give you access to most of the X-ray energies that you will need to identify your elements. You can choose a lower accelerating voltage or a higher accelerating voltage, and this will have an impact on the surface sensitivity of the technique, and it will also change which X-rays are being excited from which elements. To begin with, I've also chosen a spot number of 60. This is on the higher end because I am favoring signal over resolution. With EDX, the spatial resolution is not as good as it is with SEM, so you can favor signal and intensity rather than resolution. There's an optimization that we need to perform with the EDX system, as its working distance optimally is 10 millimeters. For SEM analysis, the optimal working distance is typically between 5 and 6 millimeters under normal conditions. So we need to increase this working distance to optimize for the EDX. And the way that we do this is by lowering the stage using the dial on the front of the instrument. If we look inside the chamber while the sample is mounted, using the chamber scope screen here, the power button is on the bottom right, we can see that when we are optimized for SEM, the sample is very close to both the backscatter electron detector and the objective lens of the electron column. This is our X-ray detector. If you follow the center line of the X-ray detector towards where the sample is, you will notice that it is actually looking below where the sample is. This doesn't give it an optimal line of sight to where the X-rays are being excited in the sample, and therefore the count rate will be lower as it is not the optimal working distance for the EDX. When we are reducing the stage position to bring it down into that optimal working distance of about 10 millimeters, you can see the sample stage moving down. And as we come down to that optimal working distance position, you'll note that now the X-ray detector has much better line of sight towards the sample where the X-rays are going to be coming from. This is the first optimization, and this is the most important to ensure that you are getting the X-rays from your sample through to the detector. Of course, operating at a longer working distance from the objective lens and from the detector will impact the SEM image, but we are optimizing for EDX, so we want to favor X-ray intensity. Always make sure, once you're done with the chamber scope, that you turn this off. The infrared light in the chamber scope camera will add a background to both your EDX measurement and it will blind the backscatter electron detector. Prepare the beam to be at the correct working distance. So I'm going to click in my electron beam settings and change the working distance to the EDS working distance by clicking this button here. You'll see that the image now goes out of focus because the beam is now focused at a working distance of 10 millimeters rather than where the sample is, which was around 5 millimeters. We're now not going to use the beam focus to bring this image back into focus, but rather we are going to lower the stage on the front of the instrument. I'm going to watch that using my reduce scan window, and I'm going to lower the stage until the image comes back into focus. To change the sample height, we use the height dial on the front of the instrument. To lower the sample position and therefore increase the working distance, we rotate counterclockwise. To raise the sample and therefore decrease the working distance, we rotate clockwise. We will then use the dial to increase the working distance by lowering the sample, and we monitor the image on the screen to bring it back into focus using the height control. Bring it into as good a focus as you can achieve, and you may need to zoom in a little bit more to see some finer details, to do some fine adjustments with the stage. Don't try to get it perfect here, just as close as you can with the stage, and then we will do a fine adjustment with the lens focusing. The sample is now in focus on the screen, and you'll notice that the number here on the dial may not actually represent 10 millimeters, but it will be nearby, often between 8 and 10 millimeters in position. I'm going to return back to my previous magnification of about 200 times. You'll also notice here that with the backscatter electron detector in particular, the intensity of the image has decreased because we have moved further away from the backscatter electron detector. So I'm going to do an auto brightness contrast to bring back the image quality. Now that we have our region of interest and we have come to the correct working distance, we are now going to prepare the EDX instrument. Power on the EDX control unit on the top of the instrument. The EDX software is on the second monitor. It is called Bruker Esprit Compact. Double-click this icon. The username and password is EDX, so click Login. Maximize this window on the monitor. The first things that we want to pay attention to here are that the software has the correct accelerating voltage being read through from the SEM instrument. Here we have 15 kV correctly noted. If this does not have the correct voltage or no voltage indicated here, it means that there is an issue with the server and the computer needs to be restarted. Also, check that you are receiving counts from your spectrometer here. This will tell you how many X-rays you are getting into the X-ray detector. Before you start, it is also a good idea to check this section of the software to see if there is any residual information from the previous user, such as sample ID or a sample coding. Click the down arrow to open this dialog and remove or change or add any information you wish here. This is metadata for your file. And additionally, check whether the previous user set up a sample coating. Or if you do have a coating on your sample, you can add this here. For example, if you had a gold coating on your sample to make it conductive, you could select gold as your coating material. This will tell the EDX software that when it detects gold, it is part of your sample coating. For my sample, I have no coating, so I'll remove this setting. There are three modes in the Esprit software: Objects, Line Scan, and Mapping. These three modes increase the data complexity, but can give you much more rich information. Objects is used for point and area analysis, where all you want is an average EDX spectrum across the area that you are analyzing. This is the simplest analysis technique. A line scan adds dimensionality to your analysis and will scan the beam across a line that you define on your sample and give you elemental profiles across that line. This is a 1D analysis technique. Mapping then expands this to 2 dimensions, and it will capture a spectrum at every pixel in the scanned area. This allows you to map the distribution of elemental intensities across your chosen area. This technique takes the longest amount of time, but can give you the most data-rich results. We will first of all begin with the objects mode. And the first step here is we want to capture an SEM image in the EDX software. Ensure that in the SEM software, the image is running and it is not frozen. Now click Capture, and we will see the image come across into the EDX software. If when you click Capture, you get a black screen, make sure the SEM software is currently scanning your image. With the image acquisition complete, we can now define analysis areas. There are 4 different analysis area types that you can choose from in the software. We have a point, a rectangle, an ellipse, and a polygon. The point analysis allows you to simply define a point on your image to capture a spectrum from. Here, the beam will not move, but it will instead be focused on this position, and you will only get a spectrum from this area. This is useful for identifying small features, grains, inclusions, and defects on your sample. Or if you just need to simply identify what a part of your image is. Rectangles and ellipses define areas. Here, you can click and drag to define a large area, and the software will capture an average spectrum from this defined area. Similarly, with an ellipse, if your features suit an elliptical shape better, you can use an ellipse to define an area instead. Finally, with a polygon, you can use this to define irregular shapes. For example, this grain here that has an unusual shape, I can define an area around that particular grain, and this will give me an average spectrum from this polygon shape. The areas that are highlighted in yellow are the ones that will be captured. So if you have multiple areas on your image that you want to capture, you need to click Select All. Additionally, if you wish to delete all of your areas, you can click Select All and Delete. Or if you wish to simply delete a particular region, click the cursor button, click on one of your regions, and then click Delete. If you need to resize an area, bring your mouse cursor over the area, click inside or click on the green border until you get a yellow outline and these anchors. Then you can click on those anchors and resize your shape, or click inside and you can move the shape. Before we click the Acquire button, we are going to check the acquisition settings by clicking on this down arrow on the button and checking the automatic modes that are set up. There are 3 automatic modes: fast, precise, and exhaustive. This increases the length of time that it takes, but gives you increasing data quality. If you just need a quick analysis where you have a high intensity of elements present, the fast analysis will be the quickest approach. If you have or are likely to have small quantities of elements present and you want the best data quality to identify those small quantities of elements, the exhaustive approach might be more appropriate, but it will take the longer amount of time. Precise is a balance between the two, balancing both speed and data quality. Choose your automatic mode and then click Acquire. We will see a spectrum appear, And quite early on, the software will identify elements that it thinks that it has detected. At this stage, the software may make mistakes, or it might miss some elements. So we can go to the Elements button here, or you can simply double-click on your spectrum to bring up the periodic table of elements. And here you can add more elements into your spectrum. If you think the software will be able to automatically ID your elements, you can click Auto ID and then allow it to add these elements into your spectrum. And then we want to make sure that these elements are correct. Alternatively, you can manually select and deselect elements in the periodic table. If a peak is missing from the identification and you need to identify which one it is, you can click on that peak to set this vertical cursor in that position and then go to the Finder tab, and it will indicate elements with X-rays nearby to that cursor position. So you can then readily identify the missing element and click on it in the list to add it back into your spectrum. If you need to see some small peaks in the background, you can click on the Y-axis, hold and drag it up to zoom in on your spectrum. You can also click on the X-axis to drag it left and right. And you can scroll the mouse wheel up and down to stretch the X-axis. Right-click on the spectrum and click Automatic Scale to reset. You can also click this Automatic Lines, Dynamic Lines checkbox to put the labels on the top of the peaks and rescale the stick patterns to match the peak intensities. Now that our acquisition is complete, we want to quantify this spectrum. Some of that information has come through to here already, as it automatically quantifies as the data are being acquired. But if you need to change elements after the acquisition, you will need to update the quantification table at the bottom. So we will come up to the Quantify button here. We're going to click the down arrow to check that it is in the automatic method, and then click the Quantify button. This will update the quantification table at the bottom. Once you've completed your analysis of the spectrum, be sure to save it in the Bruker file format. Click on the IO button, click Save, and save it to your SEM folder. To save these data out in a raw text format, right-click on the spectrum, click Save, change the file type to an Excel file, and save your file in your folder. You can then open that Excel file, right-click and copy, paste your spectrum, right-click on the SEM image, copy and paste that into the Excel file, and right-click, copy on the quantification table to save either text or bitmap into your Excel file. Moving to the line scan mode, you will see that the same SEM image that we captured previously remains in the system. If you are still in this position, you can reuse this image. If you have changed magnification or changed sample position, you must reacquire or recapture a new SEM image here. In the line scan mode, we have a horizontal line here by default. This is where the line scan will come from. When your mouse cursor is over the line and it is highlighted in yellow, click the line, and then you can click and drag on the anchors to change the angle and length of our line scan. I'm going to run a line scan across these two grains in this particular sample. And I'm also going to bring it across this inclusion in this grain here. You can see a zoomed in image of the SEM image here across where your line scan is going to be captured. You can define a point count or a distance between points with these controls. Similar to before, we can set an automatic precise acquisition time. Click Acquire and let the acquisition be performed. As the spectrum is acquired across the line scan, we see the line profiles for all of the elements across the bottom here with their overlay in the main screen. You can then click on the Spectrum tab to see the average spectrum that's being acquired. If you need to rescale that spectrum as before. And once again, we need to check the elements that are being identified in the scan. I will click the Elements button to bring up the periodic table, run an auto ID. I'm going to set my dynamic lines and check all of our elements. Since a line scan takes many more spectra, depending on the number of points that you've identified, the acquisition time will take longer. Once the analysis is complete, you can right-click and automatic scale your profile overlay here, and you can start to interrogate your line scans based on your SEM image. For example, if we want to identify what the profiles look like within these grains, we can click inside the grain here, and we will see the cursor on the profile for that part of the line scan. We can then look at which elements are increased and decreased in that part of the line scan. Similarly, at the bottom, we can identify all of the individual line scans that were present, and we can use this to enable and disable line scans in the overlay. So here we can remove elements that we're not particularly interested in, the ones that don't seem to have a significant correlation against those particular grains. I will rescale now, and we can also click and drag the y-axis here. And here what I can now see is that within this grain, we have an increased amount of titanium and also iron present. And within this little inclusion in the grain, we have increased amounts of calcium and phosphor present. So this is how you can use a line scan to help you identify what elements are present from a spatial point of view. Once again, make sure to save your data by clicking the IO button and clicking Save. Similarly, right-click on the spectrum, click Save, save your data out as an Excel file, and then right-click and copy any spectra, line scans, overlays, and SEM images that you wish to save into that Excel file. If you need to manipulate your colors after or before you've saved, you can play with the color boxes along here to make it more appealing or make it easier to understand your profiles. Now moving on to the two-dimensional mapping mode, I will click the mapping mode, and once again, we will have the same SEM image. Here, however, I'm going to make a couple of changes on the SEM. I'm more interested in this smaller region for the mapping, so I'm now going to increase my magnification to about 350 times, and I'm just going to shuffle a small amount to bring my region of interest back into the center of the screen. Additionally, because I'm going to be doing mapping, I want more X-rays to be detected. Previously, we had around 2,000 counts per second. I'm now going to increase my spot intensity from 60 up to 80 to give us a brighter image and significantly more X-rays. Do the auto brightness contrast to get back our image again. It's sensible at this stage to just double check your focus, noting that, of course, if you have increased your spot number, you will have lost some resolution and the image may be a little more fuzzy than what you previously had. And we can now see that our count rate has increased significantly up to around 14,000 counts per second. This will help us to acquire maps in a more reasonable amount of time. As we noted, we have changed position and our magnification, so we will recapture our SEM image. This box that is defined by default will be the mapping area if you use the variable mapping area mode. If you wish to change this area, hover the mouse cursor over it until it's yellow, click, and then grab the anchors just like previously, and you can redefine your map area. Alternatively, click in the middle and you can move that position. If you wish to map the entire field of view that you've chosen, you can go to the Acquire button, click the down arrow, come to the Map Area section, and click Full. Also, while you have this window open, check the map time. Note that there is no automatic mode for the mapping acquisition type, and instead we will begin with a manual acquisition to figure out how long we need to run our acquisition for. And after that point, you could define a fixed measurement time for your subsequent acquisitions. We will now click the Acquire button and start the acquisition process. The system will scan the mapped area and provide a new SEM image for the map area. It will also look at the spectrum that's being acquired, as previously in the Spectrum tab, and it will identify the elements present. Check these elements and make sure nothing has been missed or no mistakes have been made, and add and remove elements as previously. Returning back to the Map tab, we can see in the lower section the individual elemental maps, and in the main window an overlay of each of these elemental maps. Once again, you can enable and disable these in the overlay by clicking the checkbox at the bottom, removing ones that you are not necessarily interested in. To control how this map looks, or this overlay looks, I can play with the map display settings here. Often it is useful to use this enhanced color mixing, which better mixes the colors of your maps with the SEM image in the background. If you wish to simply see the EDX maps themselves without the SEM image, remove that from the overlay as well. Let the acquisition run until you are happy and comfortable that you have a high quality map. The acquisition has now been running for 15 minutes. So I'm going to click the Acquire button to let it finish at the next frame. We can now use some of these controls to play with our overlay image. For example, if we wish to change the colors of some of our elements, We can do that with the color control boxes. So for example, I might wish to make this magnesium a different color. We can also play with the map filters. Here we are applying an automatic map filter, which will average and smooth the maps to better fill out the pixels that are missing. This works well when you do have the SEM image in the background as well. But you can also choose to apply only smoothing or averaging to your maps, and then change how much smoothing and averaging is applied to the EDX maps. If you remove the filters, you will see the raw data that were acquired. Using the color controls, we can also change the gamma and the color saturation to help increase the contrast between your different elements present in the overlay map. As previously, make sure that you save your raw data file by clicking the IO button, click Save, and this will allow you to reopen and reprocess these data in the future if you wish. As previously, right-click and save your spectrum as an Excel file, and then you can copy your SEM image, overlay maps, and individual maps out into that Excel file for saving. With this extra information in the mapping feature, we can extract spectra from regions of interest. For example, we can identify that we have the calcium and phosphor present in this grain and a few of these other grains as well. So we may wish to get a spectrum from just this grain alone. We can use a polygon tool here, for example, draw a polygon around this particular grain, and this creates a new region of interest from which an average spectrum can be extracted. Return to the Spectrum tab, and we will now see that there are two spectra here identified. Click the Uncheck All, and then go down to the bottom spectrum. So this is our average spectrum from that region of interest. You can do this with an ellipse, a rectangle, a line, and a point. Once you have saved all your data, to end your EDX session, close the EDX software. Power off the EDX control unit. Return the stage height to 5.0 millimeters.